So this final section in Unit 6, which covers Chapter 8 of the book, is modeling with exponential and logarithmic functions or equations. And so by the end of this lesson, you'll be able to do a couple things. You'll be able to determine an equation for an exponential function when given 2 points, and we're going to use that generic formula y equals a times b to the x power. You'll be able to choose linear, quadratic, exponential, or logarithmic models just by looking at patterns in data. And so we'll be looking at different tables, and from the pattern you'll pick out what type of function it is. You'll also write the function, and then you'll evaluate it for any given value of x. And what we'll work on in class is applying exponential regression models to real-world data, and that'll be using your calculator. So as we go through this, be thinking about how logarithmic functions model real-world problems and their solutions. The first piece that we're going to talk about is writing exponential functions. And if we are given any 2 points, we can write an exponential function of this generic form, y equals a times b to the x power, whose graph passes through those 2 points. And I'm going to do this by using a system of equations. So I'm just going to, for this first example of 1, 6 and 2, 18, I'm just going to write in that y equals a times b to the x power And what I can do first is I can write 2 equations where I substitute the values that I was given, 1, 6, and 2, 18, for x and y. So that would be 6 is equal to a times b to the first power, and 18 is equal to a times b squared. So to be able to solve this, I want to rewrite this in terms of a. So a would be equal to 6 over b. And then I could rewrite this equation as 18 is equal to 6 over b times b squared. I can cancel out a b, and I'm left with 18 is equal to 6b, and b would be equal to 3. Alright, now I want to figure out what a would be equal to. So now I have now I have 6 is equal to a times 3, and a in this case would be equal to 2. So now I have a and b values. Now I just need to go back and write that equation and plug in my 2 solutions. So now I'll have y is equal to a was 2 times b was 3 to the x power. And so that's my exponential equation that passes through those 2 points. It's always going to be the same process, so what I want you to do is just pause the video and try to solve this next one by yourself, and then go through and check your work with what I am going to go over. Alright, so for these 2 points, 1, 20 and 3, 80, I'll start out the same way. Let me just rewrite that generic function of a times b to the x power. And now I just need to write my system of equations. So 20 equals a times b to the first power, and 80 equals a times b to the third power. So this top one, I'll rewrite as a equals 20 over b, and I'll replace that a with 20 over b, and I'm left with 80 equals 20 over b times b cubed, and I can simplify just like before. That'll be b squared. B cancels out, and I am left with 80 is equal to 20 times b squared, or 4 is b squared, so b is equal to 2. And now let's go back to this equation, and we'll say 20 is equal to a times b was 2, and so a is equal to 10. And now if I rewrite my equation using my values for a and b, I have y equals 10 times 2 to the x power. The other part of this lesson is modeling functions and looking for patterns of change. So first of all, there's some different characteristics that we're looking for in these tables. If you have, for each increase in x of 1 unit, the ratio between successive values of f of x or y is constant. So that's like saying every time I go across the table, I multiply by 2 to get from one y to the next y, or I multiply by 1/2. That means that the function you're looking at is an exponential function. And so it will take the form that f of x is equal to a times b to the x power. Now, if you have the opposite or the inverse of that, for each increase in f of x of 1 unit, the ratio between successive values of x is constant. So now this means I would be multiplying my x row by 2 or 4 or 1/4, or as long as it's constant. But now I'm talking about the inverse of the exponential function. So this would be my log. And we are going to go through specific examples of this in a minute. But be very careful when you're deciding between exponential and logarithmic, because that's where people tend to make mistakes. But that's that form, f of x is equal to log base b of x. You could have, for every increase in x of 1 unit, the first differences of f of x are constant. Now, this is when, let's say, I add 3 or add a -6 to get from one value to the next, going across my y or my f of x row. This would be linear, and it takes the general form f of x is equal to mx plus b. And finally, hopefully you remember this from Algebra 1, for each increase in x of 1 unit, the second differences in f of x are constant. We'll go through a very specific example of what that looks like, but that's your quadratic function. And that takes the form f of x from earlier this year, ax squared plus bx plus c. So we are going to look at some specific examples of tables, and for each set we want to look at the pattern and say what type of function is this? Is it linear, quadratic, exponential, or logarithmic? And then we want to actually write the function that would best model the data. So you have 4 examples on your paper, and we'll go through each one separately. Now, when you get a table like this, the first thing that I do is I just start to look for patterns in what's happening as I go across f of x. I can see that my x is increasing by 1 every single time across my table, and looking for patterns as I go across my f of x row, I'm obviously not adding anything every single time to get from cell to cell in the row, but what I'm doing is I am multiplying by 4. And that works to get from 16 to 64, and to 256, and to 1024. Now, because I'm multiplying by that constant amount every single time, this is going to be an exponential function. And now, if I want to write what that function is, this one is going to be f of x is equal to 4 to the x power. So 4 to the first power is 4, 4 to the second power is 16, 4 to the third power is 64, and so on. Now, this time that works. However, sometimes I might have an a value that's different than 1, And so if you find your rule is times 4 and then you come up with this equation 4 to the x power and that doesn't work, then you want to pick a couple of values from your table and see if we can get an a value out of it. So let's just use 1 and 4. And let's go back to that initial function that we were using, the y equals a times b to the x power. I know it's 4 to the x power times a is going to be y. So in this case, my y that I got out, my f of x, is 4, just what I circled in the table, and times a times 4 to the first power. And in this case, I end up with 4 equals 4a, or a equals 1. Which I already knew because I knew that this 4 to the x power worked, and that's just like writing 1 times 4 to the x power. But if that's not the case, if just that 4 to the x power didn't work, here's how you could go back and get your a value. And you will see examples in your practice where you need to do that. The second example of a table is where people tend to be confused, because if I'm looking through there, I automatically see this kind of this trend where I'm multiplying every time by 10. And you have a lot more experience with exponential functions, so automatically you're thinking, okay, that's an exponential function. However, it's multiplying by 10 every time across x, and across f of x or y, it's just going up 1 every time. And so this is the opposite of what we were looking at in number 1, and this is going to be our logarithmic function. And this one's changing by powers of 10, and so I can write this as, I can write this as f of x is equal to log base 10 of x, or just log x. Alright, looking at my next table, I can see right now that I have changing by 1 every time across x. So, and then if I'm looking at my row of f of x, it doesn't look like I'm adding by the same thing every time, but it also doesn't look like I'm multiplying to get from one thing to the next. So automatically you should be thinking it's quadratic. It's not changing by a constant amount every single time. And when we were going through the tables, I said when we got to, or when the previous slide, when we got to these examples, I would show you what I meant by that second difference if you don't remember. If I'm looking at this table, to get from 2 to 8, I added 6. And then I added 10 to get from 8 to 18. And then I added 14 to get from 18 to 32. And then I added 18 to get from 32 to 50. So if you don't remember, this is called the first difference. So second difference would be saying the difference between 6 and 10 is a positive 4, 10 and 14 is a positive 4, and 14 and 18 is a positive 4. So that's the second difference. And that's the definition of a quadratic function from these tables, is that the second difference is constant. So I know I'm going to be talking about some kind of a quadratic function. And how I get my a value from ax squared is I take the second difference value and I divide it by 2. So in this case, I would say f of x is 4 over 2x squared, or just 2x squared. And that would be the equation represented by this table. Finally, in this last table, I can still see that I'm increasing by 1 every time across x. And this time, as I go across y, or f of x, every single time I am adding 3. And so this is going to be my linear function. A good starting point is that this 3 is somehow going to be involved in what the rule is in our function, from making our function from our table. And so 3, let's say I can't add 3. 1 plus 3 is 4, not 5. 2 plus 3 is 5, not 8. So I'm going to start out by multiplying by 3. So I'm going to say f of x is 3x. 1 times 3 only gets me to 3. So then I need to add 2. And just to make sure that works, I would say 2 times 3 is 6, plus 2 is 8. 3 times 3 is 9, plus 2 is 11, and that works going across the table. That should be all the detail that you need to know to be able to do without the use of a graphing calculator. Much more tricky than that, you'll just use your graphing calculator and you'll use the exponential regression feature that we'll be talking about in class. But if you do want any other review, I pulled up a couple of good sites that are also on your notes if you want additional explanations. So the first one is writing exponential equations from a table, and then the second one is the same notes we're using in class to do the exponential regression on your graphing calculator, and then finally writing a quadratic equation from a table. But again, that gets into a lot more detail than you will need to know how to do without the use of a graphing calculator.